So let us come here and slide. Now, how am I going to show this? What is the method? The method is to actually, so what I will do is to write beta prime. So this is the beta prime expression for beta prime in terms of lambda prime. But what I will do is to write beta prime in terms of lambda, in terms of the previous coupling, in the original coupling, lambda. And now there are two ways of doing it. In one way of doing it, the expression in terms of lambda, the expression for beta prime in terms of lambda will have the beta I prime coefficients. In another way of calculating, it will have beta I coefficients. And then matching these two results will enable us to find relation between beta I prime and beta I primes and beta I. So that is how the calculation is to be done. So what is the way? The first way. The first way where beta prime is given by given in terms of lambda, but beta I prime coefficients. That is simply just substitute this this transformation, this redefinition, this equation here. Then every lambda prime factor power will be expressed in terms of lambda. So then the expressions will have beta I primes and alpha i's. That is the first method. So let's do that. Beta prime lambda prime is equal to beta 1 prime times lambda prime. Lambda prime is lambda plus alpha 2 lambda square plus alpha 3 lambda cube, and so on. Then beta 2 prime is lambda plus alpha 2 lambda square plus alpha 3 lambda cube, and so on to the power 2 plus beta 3 prime lambda plus alpha 2 lambda square cube. And then you basically, expand all of them. So beta 1 prime lambda plus alpha 2 beta 1 prime lambda square 3 plus beta 2 prime lambda alpha 2 beta 2 prime. Okay, so the next term is coming from here, and if you expand the binomial, you have a lambda square and the multiply and the 2ab term from this and this. So 2 alpha 2 lambda cube, this is the term. Any other term is will be this square or multiplication of lambda and lambda cube. Those are all order lambda to the power 4 order. So the first term is beta 2 lambda square, and the second term is alpha 2 beta 2 prime lambda cube. In fact, 2 alpha 2 beta 2 prime lambda cube. And from the third part, we have only one term coming up to order lambda cube, which is beta 3 prime lambda cube. Now the result is therefore beta 1 prime lambda plus alpha 2 beta 1 prime plus beta 2 prime lambda square plus alpha 3 beta 1 prime 2 alpha 2 beta 2 prime plus beta 3 prime lambda cube plus order lambda to the power 4. Okay, this is one method, and then the other method is how do you write beta prime in terms of lambda, where only beta i's appear, beta I primes don't. And that is relating, using the definition of beta prime and beta, you can relate them, and that beta prime must be given by d lambda prime d lambda times mu d lambda d mu, which is basically these two factors, and this one is nothing but beta of lambda. Beta of lambda is given in terms of lambda, where only beta I parameters appear, and d lambda prime d lambda can be written in terms of lambda, where only alpha parameters appear. So you write beta prime lambda prime to be equal to d lambda prime d lambda beta lambda. And d lambda prime d lambda is 1 plus 2 alpha 2 lambda plus 3 alpha 3 lambda square, and so on. And then this one is beta 1 lambda plus beta 2 lambda square, beta 3 lambda cube, and so on. Since this factor starts with an order of lambda, I have to expand this factor only up to lambda square, because the lambda cube order, the lambda cube term will give you at least lambda to the power 4, which we are neglecting. So now you write them as beta 1 lambda, beta 2 lambda square. The first term, 1 multiplying the second series, is this, and then the second term multiplying the series will be 2 alpha 2 beta 1 lambda square plus 2 alpha 2 beta 2 lambda cube, and so on, and 3 alpha 3 beta 1 lambda cube, and so on. Okay, and then you collect the terms beta 1 lambda plus 2 alpha 2 beta 1 plus beta 2 lambda square plus 3 alpha 3 beta 1 plus 2 alpha 2 beta 2 plus beta 3 lambda cube, and then order lambda to the power 4. So now we equate these two expressions, this expression and this expression, and then compare to find compare the coefficients at each order, and find the relation. So let me do it this way. Let me take both these two expressions on the same page so that we can compare them easily. So at a linear order, I have beta 1 prime is equal to beta 1. And then at the quadratic order, beta 2 prime is equal to beta 2 plus 2 alpha 2 beta 1 minus alpha 2 beta 1 prime, which is beta 1. So I have written beta 2. I have written beta 2 prime is equal to this expression, beta 2 plus 2 alpha 2 beta 1 minus this expression. So that is beta 2 plus alpha 2 beta 1. And then beta 3 prime would be beta 3 plus 2 alpha 2 beta 2 plus 3 alpha 3 beta 1 minus 2 alpha 2 beta 2 prime minus alpha 3 beta 1. So that's beta 3 plus 2 alpha 2 beta 2 3 alpha 3 beta 1 minus 2 alpha 2. Beta 2 prime is beta 2 minus 2 alpha 2 beta 2 minus 2 alpha 2 square beta 1. I have written 2. So basically what I'm writing is 2 alpha 2 beta 2 prime, where beta 2 prime is given by beta 2 plus alpha 2 beta 1. Right, so that's right. Then 3 alpha 3 beta 1 minus alpha 3 beta 1 is 2 alpha 3 beta 1. So the result would be beta 3. Now 2 alpha 2 beta 2 and 2 alpha 2 beta 2 cancel. So everything now. So 3 alpha 3 plus 2 alpha 3 is 5 alpha 3 minus 2 alpha 2 square beta 1. So therefore, we see that beta 2 prime and beta 3 prime will be equal to beta 2 and beta 3 if beta 1 is 0. Therefore, beta 2 prime is equal to beta 2, beta 3 prime is equal to beta 3. If beta 1 prime is equal to beta 1 is equal to 0. Now exercise as extend the calculation to order lambda to the power 4 and establish that beta 4 prime is not equal to beta 4, even if you choose, even if you have, even if this is true. Okay. Okay, so now you see, for any coupling in any other theory, if the beta function starts with this coupling relation, the relation between the two couplings, that is this perturbation expansion, is generally true. For any other situation also, any other theory also, when you do this finite ambiguities, when the finite ambiguities change because of change in the renormalization prescription, you would get an equation like this. And the result will therefore hold as long as beta function starts with lambda square. And let me now argue that that would be the case. How do we see that? So let's go to our lecture 20. Let's see the calculation of beta function. This discussion starts here, and then you show that beta function is given by this expression. Okay, where this A1 is the residue of 1 over pole in the bare coupling expansion. So I will come to that. But first, let us notice. So the question reduces to whether A1 can start with the linear in lambda or not. Okay, or is it starting from lambda square? Now, first of all, look at this expression, lambda dd lambda actually does not change the power of lambda. It is a power of lambda to the power n is an eigenfunction of this operator with eigenvalue n. So acting on lambda, it gives you lambda. Acting on lambda square, it gives you 2 lambda square, 3 lambda cube, and so on. Okay, this is what the action of this is. So if there is a linear term here, that will be cancelled between these two terms, because basically lambda dd lambda acting on lambda will give you lambda. So that is not changing. So these two terms, so it will kill the linear term. Even though actually A1 does not have a linear term in lambda, and that you can see diagrammatically also. So let us go back to the definition of A1. Here is the definition. So this is the bare parameter pole expansion of that. What was the bare parameter? Basically, this appears the lambda coefficient of 5 to the power 4 in the renormalized Lagrangian. And the renormalized Lagrangian is the original Lagrangian plus counter term Lagrangian. So this term, if you look at this term, it is lambda 0 times phi 0 to the power 4, where phi 0 is the bare field, and it's related to the original field by this z phi to the power half factor, which is basically 1 plus a to the power half. So the leading term is 1, and therefore at the leading order, phi 0 and phi are same. Therefore, at the leading order, this is nothing but the counter term Lagrangian, which is given by C. Okay, and the counter term Lagrangian is basically to kill the divergence of the 4-point function, 4.1 pi. A1, which appears in the beta function, is the residue of 1 over epsilon pole. And as we have discussed in the lecture, that a L loop term will have poles of at most order L. So an L loop term will give you 1 over epsilon, in general 1 over epsilon square, and so up to order 1 over epsilon to the power L. So 1 over epsilon pole will appear in all loop starting from L equal to 1. For all loop order, this 1 over epsilon will be generated. So A1 will receive contribution from one loop, but all loops, but the minimum loop is 1. There is no 0 loop term because it's a quantum contribution. The 0 loop term is actually the primitive vertex, which is in L, not in the counter term. So the counter term will definitely start from at least 1 loop. And now at 1 loop, can we have a linear term, linear in lambda term? That's not possible because there is a relation for 5-foot theory. The relation is V equals L plus 1, where the number of vertices is V, L is number of loops. So if you take L to be 0, then V is 1, which is this. This relation is true for the 4-point vertex. For the 2-point function, V is equal to L. Right, so V equals to L for the 2-point function, which is consistent with this diagram, where it's a linear in lambda, but it is also 1 loop. But for the 4-point vertex, the relation is this one, and when L equal to 0, you have the primitive vertex, and for L equal to 1, V must be 2, and that is what we get. This is the diagram. Different topological channels, though. There are 3 channels, but the diagram is of this sort. For L equal to 2, it should be V equal to 3. So, for example, we have this diagram. So there are 3. So there is no linear in lambda contribution to at one loop. So that's basically the argument. One has to look into the residue of the simple pole, which is A1 for the coupling constant renormalization and see at what order it starts receiving contribution. So we just argued that in the case of phi-4 theory, it receives contribution starting from lambda square, and therefore beta 1 and beta 1 prime is 0, which leads to the invariance of the beta function up to lambda cube. Lambda square and lambda cube terms are invariant under the change of renormalization prescription. And in fact, if you set beta 2 equal to 0, then one can show that beta 4 prime and beta 4 are also same. So let me extend this this exercise. So this establish this when beta 1 prime is equal to beta 1 equal to 0, and beta 4 prime is equal to beta 4, when this and beta 2 prime equals beta 2 equals 0. So basically, depending on how the beta function receives contribution at what order, certain terms in the beta function expansion will remain invariant under the change in prescription. Renormalization prescription is important because this happens both for QED and QCD. In fact, there the beta function is coupling cube and coupling to the power 5. So lambda, it's like lambda cube and lambda to the power 5 terms are there, and one can show that those two terms are the coefficients are invariant under the change of the renormalization prescription. Okay.